Right? So the last thing we did in the last lecture was to introduce the Wilson loop, which I remind you we defined to be something that has a charge Q. I'm thinking about the abelian theory here. If you want to generalize this to the non-abelian theory, this will be labeled by some representation of your non-abelian group. And it's wrapped around some path, gamma, as defined in the following way. It's the exponential of IQ integral over gamma of A. And we saw that there were some conditions. Gauge invariance of the Wilson loop as an operator required gamma to be closed. And furthermore, invariance under large gauge transformations required Q to be integrally quantized. We also saw that in the case that Q is not integrally quantized, we can still understand an object which is very similar to this one, but instead of looking at as something that's wrapped on a curve, it has a dependence on a surface. So such a thing is useful, and we'll encounter it again, I expect. All right. So one intuition for what the Wilson loop is comes from putting this in the path integral. So I have the path integral over A of my exponential of, in this case, Maxwell theory. So explicitly, something like this. Okay, so this is the standard path integral for Maxwell. And now if I insert the Wilson loop, so if I try to compute the correlator, maybe let me make a comment before I continue. Sometimes I'll write this kind of brackets as expectation values. Strictly speaking, I should divide by 1 over z. This being the partition function, that's the standard definition, so this has normalization 1. Sometimes I will forget, if I forget to include it. That's, both conventions are used in the literature, and sometimes I tend to use the one without the z. It doesn't matter too much. Okay, so here I will include it. And then if you put the Wilson loop itself, what you're doing is modifying this action, as an exponential, but by e to the q integral over gamma, so this is integral over your 4 manifold of A. So this is how you compute the expectation value of the Wilson loop, at least in principle. Oh, sorry. Early in the morning. There you go. All right. Let's look at the word identities, or if you like, the equations of motion. In this case, they're equivalent. So the equation of motion for A, how does it look like? Well, if you integrate by parts here, you get something like minus 1 over 2 E squared d of star f plus IQ. And then for writing the equation of motion, it's useful to rewrite this term as IQ integral over all of M4 of A wedge some delta function localized on gamma. Are you all familiar with delta functions? Yeah. So in this case, when you want to have a delta function localized on a curve in 4 dimensions, this is a 3 form. You can think of as a delta function in the 3 transverse coordinates. So each one is a 1 form. And then you have one direction which you don't have the delta function because the curve extends in that direction. So this is a 3 form, and this whole thing makes sense. It's a 4 form. And when I write things like this, it's immediate to write the equation of motion. This is IQ delta 3 of gamma. Okay, so, and this is equal to 0. So I can rewrite this in a bit nicer way, in this way. Okay. So if you remember your Maxwell's equations, d of a star of f, so Maxwell has d of a star of f equal to the electric current density, electric charge, which again, it's a 3 form. This thing is a 2 form. The star keeps it a 2 form. The d makes it 1 degree higher, a 3 form. So my electric charge density is a 3-form, this 3-form here. So this is how we think of the Wilson line. We have inserted some very heavy particle. There's no dynamics to this Wilson line. We decide where we put it. We decide what the gamma is, and it doesn't wiggle. But otherwise, we are testing how the theory, Maxwell theory, reacts to putting such a defect in the path integral. So we are studying how the photon reacts to a very massive particle propagating in spacetime. That's the interpretation. Okay. So that's the Wilson line, that's the basic definition. Let's see what the charge operator is, that is the operator that generates the symmetry. All right, so I'm going to call this an electric charge operator, parameterized by alpha, associated to a 2-cycle. Right? Remember the logic here. We have a 1-dimensional object in 4 dimensions. We want to measure it, so we surround it, we link it. And to link 1-dimensional objects, we need 2-dimensional objects. The total dimension should be a total dimension of spacetime minus 1. Yep. All right, so these are parameterized by 2 surfaces and parameters alpha. And it's going to be the exponential of alpha, the integral of the current, and in this case, the current, the conserved current, is integral of S star F, and this is over sigma 2.
So, excuse me. So, the general symmetry is 40 on sigma 2 because this surface links the charge operator with the default.
Correct. So this surface, in principle, is any surface, but we want that in the situation in which you have a picture like this, you generate a phase. It's e to the I alpha, the representation under the group. So indeed, if you want to link a 1-dimensional object in 4 dimensions, you need a 2-dimensional object to link it. The total dimension has to be 3, which is 4 minus 1. Yeah. Yeah. In this theory, yeah, so very good question. There are kind of 2 questions, or 2 answers I could give to that, so let me give those. One modification of this theory is if you include charged particles, dynamic charged particles. In that case, the condition doesn't hold anymore. You can have a Wilson loop that ends on a charged particle. That's what we have in nature. So the electron is not gauge invariant under the U1, but we keep talking about electrons. So what's a good way of thinking about that? You think about an open Wilson loop coming from infinity and ending on the electron, and that's a gauge invariant object that you can think about doing experiments with. And that relates to your second question, can the Wilson loop go to infinity? Yes, it can, if you have an uncompact space. Typically, when you do a gauge transformation, you don't impose that gauge transformations at infinity are gauge transformations. You can allow them to be global symmetries of the system. They can act on the Hilbert space. So in the particular case of Maxwell, indeed, the U1 transformation of Maxwell at infinity is not a gauge symmetry, it's a global symmetry that is the thing that measures the electric charge of the system. Yeah, very good. Any other questions? Okay. So I want to highlight a point that's normally not highlighted, but it's a bit of an annoying bit. Okay. I didn't put an I here. Generally, I define this as exponential of I alpha the charge, or the current. And the reason for that is because there's an I here. And what I want to do is to have an operator that when it acts on the line gives me a phase e to the I alpha. So the I here is very natural. The analytic continuation from the Lorentzian of the Wilson loop needs to have an I for gauge invariance, basically. So that requires that my operator does not have an I. It's not important because in the Euclidean, my operators don't have to be unitary. Unitary is a concept for the Lorentzian. But if you're confused about the lack of I, that's the origin. Okay? And we'll encounter this I in many places. For example, when I study S-duality, you will see that this operator defined at this is really the S-dual of the operator I will introduce in a second, the magnetic charge operator. Right. So let me support what I just said. This operator written like this is the one that acts with the e to the alpha. And the idea is using this equation. So if I have this sigma 2 that links in this way, we can construct D3 here, such that the boundary of D3 is sigma 2. And then I can write this equation in this setting. I use the word identity with the Wilson loop, charge Q on gamma. So I can write this as exponential of alpha integral of boundary of D3 of star F times Wilson loop. Now here I write this as exponential of alpha d star F over all D3. So I translate into an integral here in interior. And now I use this relation here, this one here. That tells me that this goes as e exponential of 2 pi I, there's factors there. Q alpha times the Wilson loop. There's no 2 pi, sorry. Okay. So the I is in place, and that's what I want to see. There's some factors of E square and so on that you can absorb in the star F, so I'm sort of ignoring it. I'm choosing conventions so things work out. So please forgive my sloppiness here, but you can fix the factors. Yeah. Okay, there was a question yesterday, which I want to answer again because I thought it was interesting. And it comes from the fact that sometimes when I do this kind of argument, I choose some disk whose boundary is sigma 2, the place where I'm putting the operator. But very often I have more than one choice. And a particularly interesting configuration is when you have a charged operator in a compact space. So I'll do an example, but the general picture should be clear. So let me do it for the Wilson loop. So take example, my manifold to be S1 times S3. Okay. And I'm going to wrap my Wilson loop on the S1. So the picture looks a bit like this. You have an S1, you have an S3, and wrap my Wilson loop in here. Just gamma here is the S1 factor times a point in S3. So a point here. So we have a picture like this. And let's try to measure the charge of this operator. Well, I can pick a sigma 2 around it, like this. And I just proved for you that you compute the electric charge operator on this sigma 2, acting on the Wilson loop. So what is it? Well, I can construct this disk. It intersects the point. So we call this disk here dA. This is a 3-disk. It's a 3-ball if you want. And this gives e to the I q alpha times omega q alpha. And again, this should all be understood inside the correlation function, of course. So this is e to the I q alpha omega q of gamma, wq of gamma. Okay, so that's one thing I could choose by choosing dA. But there's obviously an alternative choice, which is the ball that's in the outside of sigma 2. Instead of contracting inwards, I kind of close it to the outside. So let me call that dB3. There's a 3-ball that has the same boundary. If I take the union of dA and dB, I get the whole 3 sphere. So if you want, you can characterize this as the closure of S3 minus dA. Right? So subtract dA and then add back the boundary. That's basically what I'm doing. And if you take both, you get an S3. So this is a perfectly fine thing I can do. And it also has the same boundary, so I could run the same argument. But now there's no intersection between my charge operator and the disk. So if you like, what I'm doing is taking this operator and closing it in this way. So in this case, what I get is the expectation value of the Wilson loop in this configuration is identical to expectation value times an arbitrary phase. These two things are identical, and this implies that the expectation value of the Wilson loop in this configuration is 0. So this is a version of the familiar statement, perhaps familiar, that if you put a charged operator in a compact space, the expectation value is 0. Anytime you measure something charged, you have the option of going to a non-compact space or to put some witnesses far away that have a charge which is opposite to the charge of the operators you want to measure. What else can I say? Maybe one thing I could say is that you might be confused when I later on in the lectures, I start talking about the expectation value of the Wilson loop. When I do that, and I show to you that the expectation value of the Wilson loop is not 0, I will do that in a non-compact space. So that's the loophole I will be using when I show the expectation value of the Wilson loop being non-zero. Yep. Mm-hmm. No, I could do a point operator, for example, in a compact 4-dimensional space or in a 5-dimensional space. Hmm. Yeah.
And I consider two codes like this.
Yeah.
Then doesn't matter how I choose to close my surface, we will use the grid.
Two curves like this. Yeah, that's a bit different because you don't have this choice of opening the outside or in the inside, right?
But it's still a compact manifold.
It's still a compact manifold, yes. But that's yeah, that's a good point. So when I say a charged operator, what I mean is wrapping a cohomology. I haven't defined cohomology. It's wrapping a cycle that you cannot deform to the identity. So in this case, that's why I wrapped the next one, and this is a point. So I could do, for example, points in 4 dimensions. You cannot deform points to 0. You cannot deform this kind of product to 0, but in your configuration, if, for example, one of these is the charge operator, and I take it out, the other one can contract to 0 and carries no net charge in this sense. It can be continuously connected to the identity field. Yeah. Thank you. Any other questions? Very good. So let me say something about the magnetic symmetry. We found, as we were thinking out this Wilson line, we found that there was another surface operator, this one here, that if you remember, looked like e to the I integral of f. And this was also topological. So I'm going to define a magnetic charge operator. So it's parameterized by some alpha, again, and some curve. And it's defined to be the exponential of e to the alpha, sorry, e alpha integral over the curve of f. Okay, this one is topological. That's quite clear. So because df is equal to 0 in vacuum, so if I do nothing else in the standard vacuum, df is equal to 0, m alpha of sigma 2 is topological. And the question is, what is this thing measuring? We have a charge operator. It will be very convenient if it's actually measuring something. So for that, I'm going to discuss, to try to understand better what is going on in this case, I'm going to discuss a little bit about the one duality that Maxwell theory has, which is known as electromagnetic duality. It's electromagnetic. One reason for that is that classically, so let's go back for a second to classical mechanics. The Maxwell equations are d star f equal to 0 and df equal to 0. And these equations, again in the absence of sources, these equations have a symmetry in which you exchange f and star f. In fact, they have a much larger symmetry. I could rotate, if I think of f and star f as the components of a 2 vector, I can rotate them as I want. D is a linear operator. So the question is, does this symmetry survive in the quantum theory? And it's a quite magical statement that it does. It was not guaranteed. For example, the symmetry as mentioned, in which you rotate this as a 2 vector, is not preserved in the quantum theory. It's only a discrete subgroup that survives. I'm going to give the argument ignoring some subtleties. I will highlight the subtleties, but I will just tell you the answer without calculating it. If you want to see the details of the argument I'm going to do, there's an old paper by Witten. So that's HepTH 95. And a more recent paper by Xie, Tachikawa, and Yanekura, which takes some topological subtleties in a very nice way. So if you start thinking of what I said and you run into some of some things that you don't understand, you can go to these papers, and there's a good chance it will be explained in detail in there. Right. So let's go back to Maxwell theory. This is my theory. And when I write Maxwell theory in the quantum theory, let's be a little bit careful about what I mean now. F is the curvature for a U1 bundle with connection A. So very often we write something like F equal to dA. Here I have to start being a little bit careful because A might not be globally defined. It's not a differential form. It's a connection in a bundle. This bundle has curvature F, which is a two-form. So this one is fine. This one is not two-form. And it's not only a two-form, but it's actually integrally quantized. Okay. I think for some of you, when you see this expression with the discussion yesterday, you might start thinking, oh, large gauge transformation or gauge transformation, right? So the discussion I will do will put that in a firmer footing. It's actually, you can think of the F as some gauge transformation parameter. So to see that a little bit better, let's write a theory. I'm going to write it SD, so define a new theory. I'm going to put new in quotes. You'll see why in a second. With fields A, and the A is the same one as here, so this is a connection in a U1 bundle. AD, this is a connection on a U1 bundle. And finally, a field that called B, I think. B. This is a bit more exotic. This is a connection on a higher U1 bundle. So what this means, without using fancy language, this is locally a two-form with gauge transformations B goes to B plus d lambda, and lambda here is a one-form connection. Okay, so B is sort of the same thing as A and AD, but it has two indices instead of one. Another thing to keep in mind is that in the same way that that A and AD had gauge transformations, this one has gauge transformation, but the gauge transformation parameter isn't necessarily one form, it's actually a connection. If I was more precise, actually, I should have written that this object here is in omega 2 with integrally quantized coefficients, so integrally quantized periods. Okay, so I will write d lambda, but you should always understand that what I mean is an objective. It's a gauge transformation, potentially a large one, of such a connection to form. All right. So these are my fields. I have an action which goes as follows. 1 over 2a squared, integral of f minus b, which star of f minus b, plus 1 over 2 pi I integral of b, which ft. Let's see if I got the signs right. Yeah. All right. So what are the gauge transformations here? There's a simple one, which is AD goes to AD plus D alpha, and AF invariant, sorry, A and F, A and B invariant. That's the first one. And again, I'm going to use this notation because it's conventional, but don't take the D alpha too seriously. What this means is, again, form with integral periods, in this case, omega 1 with integral periods. Okay, it could be a small or a large case transformation. Okay, so this is clearly a gauge. This is an invariance of this action because AD only appears inside FD, and FD is completely gauge invariant, so that's fine. And there's another one which is more exotic. It goes as follows. I send B, I do a gauge transformation of B, call it beta. But then this term changes. So I'm going to compensate it with doing a shift of this one. A goes to A plus beta. Now you might wonder about this term. The change in this term is going to be d beta, so let me say it, the invariant. Now the change on this term is going to be B wedge FD goes to B wedge FD plus D alpha wedge FD, and by parts, this is integral of F wedge, sorry, integral of B wedge FD plus signs, integral of alpha wedge DFD, and this is 0. Okay, so this term, despite appearances, is also gauge invariant under this transformation. Sorry? I integrated by parts. So here I'm assuming that the manifold when I'm defining this theory is compact. If not, I have to worry what happens at infinity. The standard thing is putting the gauge transformation to 0 at infinity, in which case I have the same argument. Once you accept that I can integrate by parts and not get a boundary term, then what I'm left with is this term here. And d of fd is 0, because fd is a curvature of AD. Oh, maybe, sorry. Just to be completely clear, fd here is the AD. And this term is, in that way, gauge invariant. Okay, so one of the things you might be a little puzzled about here, I'm making a big deal about these things being potentially large gauge transformations. I have defined this with a D here, and it seems not so obvious how to define this term in that way, if I'm thinking of the large gauge transformations. So doing that carefully is one of the things they do in this paper. So if you're interested, do take a look in there. All right, so here's the claim. This theory is equivalent to Maxwell theory. So despite appearances and putting all these many fields and so on, this theory is exactly the same quantum mechanically as Maxwell theory. Okay, let's prove it. So FD or AD appears linearly. So it's a Lagrange multiplier. So in the path integral, whenever I have a Lagrange multiplier. Oh yeah, sorry. Yes.
I don't understand the difference between the connection A and the connection R. They are both connection and one bundle.
Yeah. Well, you have two U1 bundles. We have three. You have these two which are standard and this one which is higher. And these are connections on the respective U1 bundles. So if you want, you can think of U1 times U1 times higher U1. Yeah. Mm-hmm. So this looks like a very different theory, right? I have like two U1s and an extra weird generalized U1, and the action is like this. But the couplings are cooked in such a way that this will all boil down to the standard Maxwell theory. But a priori, they are different things. You will see in a minute, once I finish my argument, that the relation between A and AD is that you can think of A as the electric connection and AD as the magnetic connection. So in the standard formulation of Maxwell, we pick one. We say this is my electric A, and we never define an AD, an A dual. Typically, we cannot. But one of the virtues of this is that we can see both at the same time, and we can play with both at the same time. The reason for this is because I want to understand what happens to the Wilson loop. And with this argument, I'll be able to go from one description to the other. So let me get there, but yeah, these are two different things a priori. Mm-hmm. Right. So whenever you have a Lagrange multiplier in a quantum field theory, something that appears linearly in your action, you can do the path integral explicitly, and what this means is that you impose the equations of motion, you impose the constraints that appear from the Lagrange multiplier. So what are the constraints that appear from the Lagrange multiplier? So integrating by parts, we have something like integral of dB wedge AD. So the equation of motion, if I have such a globally defined AD, is that dB is equal to 0. So B is closed. Or more precisely, perhaps, the field strength in this bundle has to be 0. It has to be a flat bundle. All right. So flat bundles are classified by their holonomies up to gauge transformations. So this is the statement I've made before, that if you have bundle engineering, you need to understand the curvature and the holonomies. They're related, but not quite the same thing. But if you don't have any curvature, all the information you have in a gauge bundle is the holonomies. If you know all the Wilson lines in your theory, you know everything there is to know about your bundle. In this case, I have a flat bundle because of that constraint. So let's think about what remains. I have something like the exponential of 1 over 2 pi I integral of B, which ft. And I want to do the integral over all ft. I have already said that my B is flat. So this is the sum over topological sectors of ft. I already took care of the local dynamics. When I wrote this argument implicitly, I was assuming that I can define globally one form connection AD. So this would be the case of a trivial bundle. But if the topology of the bundle is non-trivial, and in the path integral I sum over all topologies, I'm still left with the sum over topologies, sum over topological classes. So the topological sectors of a U1 bundle, like Fd, are parameterized by integers on 2 cycles. So this is the same thing as saying that if you use path integral, you'll get that the integral of the holonomy on the do you all know what Poincare dual means? Sorry, can you raise your hand if you don't know what Poincare dual is? If you don't, then negative. You don't know what Poincare dual is? No, perfect. So let me do that. So it is a bit out of order, but I need it at this step of the argument. All right, so remember that when you have a differential form, you have an operator D, which maps differential form of degree P to differential forms of degree P plus 1. You can define something known as the RAM cohomology group of degree P of your manifold. So it's the RAM cohomology. And this is defined to be the closed forms. So that's the kernel of D acting on omega P. So those forms which are closed, modulo the forms that are exact. So those are the image of the D operator acting on omega P minus 1. So Poincare duality is a statement out elements of this group. It's a map. It goes in both directions. It's invertible. It goes from H, the RAM P on M to H P of M with real coefficients. So I have to define what this is. What this thing is the same sort of definition. Is the kernel of the boundary operator acting on P manifolds modulo the image of the boundary operator acting on P minus 1 manifolds. Yep. Thank you. Yes. Yeah. All right. So this is something that's defined in the same way. You can think of as the definition is saying take the manifolds that don't have a boundary, and those that are at the boundary of something, treat them as trivial. Thank you. Yes. I should improvise this thing. Sorry, apologies. D minus P. You're completely right. All right. So this is a Poincare duality statement of this type, and in practice, what it means is that you can replace, there's a one-to-one map between, let's go this way. If you give me a D minus P manifold in space-time, which is closed, I can replace it by some P form. And what's the P form is basically a delta function, or some smoothing of the delta function, localized on the manifold. So it's a map, if you want. It's a map from manifolds in that sense, so objects in that quotient, to delta function on the manifold. Sometimes this is called Poincare duality and this is called Poincare duality inverse. They are isomorphic, so conventions vary, but that's what it means. Okay, so now I can come. Thank you. That was a bit quick. I'm more than happy to discuss after the lecture. You have more questions. And in any case, in probably the next lecture or the lecture after that, I'll define this much more carefully and in more generality. Okay. This was just a quick reminder. Okay. Now that I'm over topological sectors, notice that this is closed. This is closed, and if you remember your differential forms, you know that the integral of closed wedge closed reduces to a product in the RAM cohomology. So this is the Sensu product in the cohomology classes, and then I use Poincare duality. So this becomes the Poincare dual of fd. I removed a factor of 2 pi because typically in physics, we take the convention fd is 2 pi quantized, but we take the integral basis for cycles. So the 2 pi went there. Okay, and what the Lagrange multiplier is telling me is that this has to be 1 for all fd. So what this implies, sorry, just to give it a name in case this kind of argument is not familiar, this is a representation of the Dirac-Combs function. Are you familiar with this term? So if you have basically the sum of overall n of an exponential of something times n, and you sum over n's, the something localizes over the integers. That's called the Dirac-Combs. So what this means is that, in particular, the periods of B are quantized. They have to be 2 pi I times an integer. So B belongs to this class. It has to be two form with integral quantized periods. All right, so that's very nice because what we are saying then is that B, once you impose the Lagrange multiplier, it has to be pure gauge. Okay. So I can write this as saying that B is pure gauge. So gauging B away. Through this transformation, I end up with S Maxwell. Okay, so after all, this was Maxwell theory.
So repeat your argument why the B is 0. And you integrate by parts.
Do what? This B? This part here?
Yes.
Yeah. I start with this coupling here. Let me assume that F is topologically trivial, meaning that it's D of a globally defined form. That's definitely something that is in the path integral. And let me write it in this way, D of AD. Then I can integrate by parts, put a D here, and I get this coupling here, DB, which AD. This is a Lagrange multiplier, something that appears linearly in the action. So I can integrate over this dA, and what it does is impose a delta function and localizes you on the solution of the equations of motion. It localizes you on dB equal to 0. So the argument, similarly to what I did here, it's using this kind of argument. If you take the integral over dx of e to the px, this is delta of p. When you have something that appears linearly, what this induces in the path integral is a delta function that localizes you in the in here. Yeah. So now I can do the path integral in this localized sector for the flat connections, and I'm still left with a little bit of information from the F, which comes from the fact that F does not have to be topologically trivial. You can have a non-trivial element of cohomology, inter-RAM cohomology, and you're left with an integral of this type, which is basically exponential of some factors with I, a b times an integer. So this forces b to be an integer. Again, if this is not familiar, look up the words Dirac comp. It's basically what this happens. If instead of integrating over x, you sum over integral n's, maybe soy right. If this is not familiar, if you sum over n e to the ip n, this is a sum over k up to factors, sum over k of Dirac of k. And k here is integral. Okay. Right. This is all to say that I wrote Maxwell in a very complicated way. But what's the point of doing that is that now I can do a different integral. So approach 2. Oh dear. No. Okay. Let's start with SD. And notice that f itself is a two-form with integrally quantized periods. So from the point of view of this gauge transformation, it's just pure gauge. If I do this kind of transformation, I can gauge f away. So our familiar electromagnetic field, the F, from this point of view, is nothing but a gauge parameter that took some life. So we get some SD prime, say, which is 1 over 2e squared, integral of b wedge star b, plus 1 over 2 pi I, integral of b wedge ft. Now, this might seem a little bit pathological because you might think that this is not gauge invariant, the B, but I already took care of the gauge invariance by gauging F away. So there's no gauge invariance left. Now, this is quadratic in B. So I can integrate B out. Right? This is a Gaussian integral. We know how to do that. If we know how to do one thing in physics, it's Gaussian integrals. So this is a Gaussian integral. And then you end up with a theory that looks like this. If you complete the square, basically what you get is E squared over 2 integral of FD wedge star FD. I should say that when you do a Gaussian integral, first you do the classical Gaussian integral, which gives you this very straightforwardly. You complete the square, basically, and then integrate on B. But you also have a one-loop term that I did not write. It's computed carefully in this paper, for example. It's not going to affect anything I say. So we came back to Maxwell. But now this is a Maxwell that looks different. This is a Maxwell with a coupling E squared. So this is the magnetic description. Okay. Why do I say the words magnetic? Maybe, sorry, I put in my notes, maybe this is a good time for you to do a small exercise. So generalize this to a non-trivial theta angle. So this coupling in Maxwell, which looks like the factors. So you can actually run the whole argument again, including the theta angle, and the details are worked out in this paper by Witten. It's a good exercise. Okay. So in the theory, SD, the equation of motion for B is something like the following. You get a B which star FP from the kinetic term with some factors, and an FD from that term then, since I must like term. So hopefully I got the factors right when I did the calculation. So this is the equation of motion for B. This justifies the word magnetic I used here, because up to this gauge invariance between B and F, I can think of this equation as saying me that F dual is some constant times I times star of F. So what was electric for F is going to be magnetic for FT. The Hodge star changes places. So in terms of operators, if I have a Wilson line operator here, so something that goes with e to the integral of star of F, and their duality, or let's do this by steps, introducing B. Once I introduce B, this is no longer gauge invariant, so I have to put the gauge invariant coupling. The Wilson loop operator will look like e to the integral star F minus B. And then going to the AD description, this becomes e to the up to factors, so if I can do it right, integral of I, integral of ft. Again, up to factors that I'm being a little bit sloppy about. But this is the old friend. This is the object that we wanted to understand. This is the integral over 2 surface of f. In this case, I'm calling f fd, but this is the integral over 2 surface. Okay. So now we have a definition of what the charged object is by tracing this duality argument. Here, the charged object was the Wilson line on gamma. So this is, am I being too small? Thank you. So this is I q integral of A of gamma. I'm not going to write what it is. Here is basically an object like this, but now notice that because of gauge invariance, it has to see a little bit of B, so it's not entirely straightforward to describe what this is. But it is simple again here. It's going to be the, well, it's hard to describe in here, sorry. But if I do the other way around, the object I actually wanted to construct, So if I start with this object, that's charged under e to the I integral of f, under duality, it becomes the Wilson line in the dual variables. Charged under e to the star of f dual. So this is e to the I integral over gamma of f dual. Okay, so the object charged in this way under the original field becomes a Wilson line for the dual field. Basically, we're running this sort of argument backwards. I knew what happened to the Wilson line in here. It becomes a sort of funny object that's charged under the magnetically under the dual photon. So the one that's charged magnetically under the original photon has to become a Wilson line in the dual description. Okay, so this is an example of something known as a top line. There's various ways of describing this kind of object. The simplest, perhaps more straightforward way is to say that this is a very massive monopole. Very massive monopole probe. So what does this mean? Imagine you have a three-dimensional space, and you put a monopole, and you drag it through time, so you get a picture like that. And how you detect that you have a monopole in a three-dimensional slice, you surround the monopole particle by some 2 sphere, and you measure f over the 2 sphere. And you get 1, or whatever you get. So the integral of f on an S2 here, we call this sigma 2 perhaps, is the amount of magnetic charge. Okay. So this is in general, because f is quantized, this is some multiple of 2 pi, integral multiple of 2 pi. I'm going to write this as 2 pi n. So these top lines, they're often written as something like h n of gamma, where n indicates how much monopole charge you have there, how non-trivial the bundle is around this object. And it dualizes to a Wilson line in the dual with charge n. Okay, any questions? Notice that this is something that's not so obvious how to define from a purely electric description. From this description is specified by the boundary conditions of the A field on the line. Not quite just the integral of A or anything like that. We are saying that the integral of f around it has to have a fixed value. As we contract the surface sigma 2 to smaller and smaller spheres around this line, for the integral to be constant, we see that f needs to diverge close to the line. So this has a singular behavior around this line. So it's not so easy to define, but from this electric magnetic duality argument, we can understand it a little bit better. Okay, so let me write the summary. What we have learned so far about Maxwell theory. It has symmetry U1 electric cross U1 magnetic. They're both one-form symmetries. The real symmetry group is a little bit bigger, but let me not go into that. At least at the level of one form, something like this, generated by the electric charge operator, so parameterized by an alpha and some two surface. Just the exponential of alpha integral of f. And another one, you see here, m alpha sigma 2, the exponential of I alpha integral of f. And the charge objects the Wilson line is charged with respect to the electric one. And the top line charged on this one. Okay. Any questions so far? Okay, so we have enough technology for one of the first, to me, important results, how it generates global symmetries. It's very easy to get lost in this field and become more and more formal and so on, try to obtain more and more complicated algebraic structures. But in the end, what we really want as physicists is obtain dynamical information out of theories. And here's probably the simplest result I know, which is, I think, very, very cool. So this is something I can already explain, this theory, the Goldstone's theorem. For higher form symmetries. And of course, if I want the Goldstone theorem, I want continuous higher form symmetries. So there's lots of literature on this. In fact, as far as I can tell, this goes back to Polyakov. Before I was born, Rosenstein and Eliezer and Kovner. In 91, so probably before you were born. And then Gayotto, Kapustin, Seiber and Willett. They pointed this out again in a more systematic way and closer to the way I will describe. And my treatment is going to be based on a couple of papers. The first one is a paper by Lake. The one I'm going to be following quite closely is the one by Nabil and Diego. So this is 2. Okay, so a really pretty paper I want to follow, although the basic punchline and the physical understanding was already advanced in many of these papers. So I want to understand something about Goldstone's theorem for these higher form symmetries. And if you remember Goldstone's theorem, it tells you that whenever a symmetry is spontaneously broken, then there's a massless field. So if I'm going to say something interesting, it must be the case that at least one of these symmetries is spontaneously broken. Spontaneous breaking, in general, means that you have a charge operator who gets a BEV in the vacuum that you have. I proved to you before that in a compact space, this cannot really happen. At least if the operator has non-trivial charge, it cannot collapse to zero. So I'm going to go to non-compact space. I'm going to take my 4 manifold to be R4. And let me try to argue that there is a spontaneous breaking in Maxwell theory for one of these symmetries. In fact, both of them will be spontaneously broken. So let's try to compute the expectation value of the Wilson loop in R4. And this will come back to some of the questions that were asked before about boundary conditions and going to infinity and so on. So I'm interested in showing that some operator which is charged has a BEV. As long as if I find one, I can make an argument. So let me choose a convenient one to start with. I'm going to choose something like this. So my gamma, my curve where I'm going to compute the expectation value of the Wilson loop, is going to be of this shape. It has a length tau in the Euclidean time direction, and spread R in one of the spatial R4. This is, of course, totally artificial, what I call time and space. Doesn't matter, just to have a mental picture. All right, so let's try to compute the Wilson line correlator. I'm going to give you a heuristic argument. The details will take me too long. But if you want to see them, you can go to chapter 42, and there's not a typo, of the lecture notes by Srednicki. Where he works out all the details with photon propagators and so on. I'm just going to sketch why his calculation does, or what is his calculation doing. All right, so if I think of this in the following way, remember that the Wilson loop, we could think of it as the insertion of a very massive probe particle. So I can interpret this diagram as nucleating, sometime in the past, a pair of particle-antiparticle. So I have some orientation in this loop. So I propagate a pair of oppositely charged particles. I evolve in the future for a while, and I let them annihilate. Also, remember another thing I said, that when you're computing a path integral in this kind of long cylinder-like geometries, what you're computing is the time evolution of the Hamiltonian. So this is going to be approximately, for large tau and r, something like e to the minus tau of the energy of the ground state. So minus tau Hamiltonian. And for large r, that's tau, this is the e to the minus tau energy of the ground state. Okay. So this would be the Hamiltonian in the presence of these sources. They introduce some energy in the system, but otherwise we have the standard argument that this is Hamiltonian evolution. And the only thing I need to worry about is how much is the ground state energy in this system. So where does the ground state energy come from? Well, I have a Coulomb potential between these charged particles. So there's an energy that goes as 1 over r up to constants. Yep. There's no kinetic energy. These are things that are rigid. But there's also some term here. I'm going to call it 1 over a, which is the self-energy of the charged particles. So when you have, in electromagnetism, a charged particle propagating, and you start computing the energy, you actually get a divergence. The self-energy is infinite, so you have to regulate it. So I'm going to put a cutoff, which is A. So A is some UV cutoff that makes this computation finite. The self-energy of the charged particle, I make it finite by introducing some cutoff. So in the limit, in which A is much smaller than R, much smaller than tau, so the UV cutoff shouldn't be comparable to any of the characteristic distances here. And I want to have a lot of evolution in time and not so much nucleation time. Okay, that's the idea. The BEV of the Wilson line and this particular path. Is going to go like e to the minus tau divided by a. Up to factors. So one thing you could worry is basically what I'm computing here are propagators of the photon from here to here, and from here to here. You can ask what happens with the propagator of the photon from here to here. It's going to be very suppressed because of my assumptions. These things are very far. You can worry what happens propagator of photon from here to here. Again, that's going to be dominated by these contributions here. And here to here, again, dominated because of the assumptions. So that's the leading behavior. So this is an example of perimeter law. You see that the correlator of this goes with, up to a constant, the length of the path that the particle is describing. This is a characteristic test of a Coulomb phase. These words might not mean much, but we'll come back to them probably when we study non-abelian theory, which behaves in a different way. The non-abelian theory has confinement, and this kind of formula is no longer correct. Okay, so if I have this behavior, define some new operator, which is basically e to the tau over a, omega q of lambda. So why can I do this? Notice that this is a local counter term. This goes with the length, so I can introduce a term like this simply by measuring the length and multiplying by a. So this is a term that I can write locally in the action of the Wilson line. It's a local counter term in my theory. So this is a well-defined local operator that I can define this way, and this one has expectation value 1. Okay, so taking r to infinity, but keeping all these approximations, so in some scaling limit, I have a picture that looks like this, an infinite Wilson loop. This is the dressed Wilson loop. And the expectation of this dressed Wilson loop on this vacuum is 1. Now I can compute how this Wilson loop is charged. So this is an example of the question that was asked before about two linking curves. I'm linking one of the components here to construct the charge. If I were to link both, I wouldn't have a spontaneous symmetry breaker. I have to link one, but to talk about an operator in one, I have to decompactify in this way. Right, so if I take this dielectric charge operator with an alpha and this sigma 2, in this case it could be an S2, for example, I get that this is e to the I alpha expectation value. Okay. So this is a case in which the expectation value is not 0 and it transforms non-trivial. This is Goldstone's theorem. I can apply Goldstone's theorem. Well, at least if there was a Goldstone theorem for higher form symmetries. So let's see. This is quite a standard. Let's see how Nabil and Diego argue from this point on. So they have this construction. They have constructed this operator. And they want to see that there is some sort of Goldstone boson in here. So I didn't forget anything. Okay, so this expectation value was 1, so I have that, of course, with the QAs. Right, so we're almost in business. Let me summarize what I found. I found that the integral of the exponential here, so this is the exponential of alpha integral of f times the Wilson loop is e to the alpha times q. Now take the derivative respect to alpha. So here's where I'm using that this symmetry is continuous. I wouldn't be able to do this if I was in the discrete symmetry case. And in fact, there's no Goldstone boson for discrete symmetries. So here's the step that generally fails. You get that the integral, and let me be a bit explicit here, over the S2 where I'm integrating, this S2 in here, of star f this quantity here. And let me go back to the language of standard integrals. So I have something like this. Mm-hmm. Oh, yeah, sorry. I derive with respect to alpha. And I looked at the first term in the expansion. So I took the, if you want, the Taylor expansion with respect to this. And I looked at the first term. Equivalently, yeah, I said derivative and then alpha equal to 0. Mm-hmm. Yeah. All right. So this problem has rotational symmetry. On the S2. Right, so if I rotate the configuration S2, I get something identical. So the propagator of this kind of correlator, I'm computing here, has to go as some function of R, where R is the distance in here. Okay, so let me take a sphere around the origin, and this propagator has to go with R. But if it goes with R, this object is a constant. I can take it out of the integral. And then I have simply the volume of the integral. So up to factors, I get that this thing, f of r times 4 pi r squared is iq. So this implies that f of r goes like 1 over r squared. So what have I learned? If I compute the correlator between, let me draw it again. I have my Wilson line, I have my symmetry generator here, and I'm computing a correlator in the Maxwell theory between a point here on the sphere and a point on the line. And I'm learning that this propagator goes as 1 over r squared. So whenever you have a propagator that goes like this, you have a pole in the S matrix, it means that you have a massless particle. So this kind of behavior, this implies the existence of a massless particle. There's the, if the particles are massive, what you have is Yukawa interaction that decays exponentially. You're not going to get that. So the only way you get this kind of behavior is with a massless particle. So this very neat argument shows, indeed, that there's a Goldstone theorem in this case. There has to be a massless particle in this configuration. And this configuration is nothing but Maxwell theory with some operators inserted. So there has to be a massless particle in Maxwell theory. But we only know one, right? It's the photon. So in this interpretation, we have that the photon is a Goldstone boson. Of a spontaneously broken one-form symmetry. Okay, to me this is very satisfying. It's a theorem I like a lot. Because anytime you see anything massless in physics, you should try to understand why it's massless. Very often we give the answer it's massless because of gauge invariance, but that's kind of a circular argument. We use gauge invariant to model massless fields in a consistent way, in a Lorentz covariant way. This gives an intrinsic reason why the photon in Maxwell needs to be massless. There's no quantum corrections that you could do in the system that will make it massive because there's a broken one-form symmetry. Goldstone's theorem is exact. It's a quantum theorem. So the only way to give mass to the boson is to break this symmetry somehow or stop the spontaneous breaking from happening. Okay, so you either don't have the symmetry or it's not spontaneously broken. But if it's spontaneously broken and a good symmetry, you need to have the photon massless, exactly massless. Any questions?
Does it hold for every dimension or only in phosphor?
No, it works in any dimension. So I was a little bit quick with the form of this propagator. The form of this propagator will change in a dimension-dependent way, but that's what propagators do in general dimensions. So if you look at the propagation of a one form in 10 dimensions or something, you have a different power, but there's a power that makes this calculation still work in 10 dimensions.
How does it work in 2 dimensions? Because I've seen that QED in 2 dimensions has a massive.
Yeah, 2 dimensions are a bit funny always. Yeah. I'm not going to say much. The one-form symmetries in the problem with 2 dimensions is one-form symmetries are like. I'm not saying anything. It's just different. Yeah, we can discuss later. Yeah.
And what about the two polarization of the photon? I mean, how do you handle that?
Yeah, yeah, that's a very good question. So maybe that links to the next thing I was thinking about discussing briefly, which is what happens in QED once you include dynamical particles. Because in that case, one of the symmetries, the electric symmetry, is broken, and you still have a massless photon. So to answer your question directly, what happens is that this argument I just gave you tells you there is a massless particle. If you run the same argument for the magnetic symmetry, so the top line and magnetic symmetry, it tells you there is a massless particle. It doesn't tell you have to be different massless particles, and in fact, the calculation is saturated for the photon. So the photon is the Goldstone for both, sort of. Yeah. So let's do the case of QED. In QED, we add charged particles, of charge Q, as I say, dynamical charged particles, charged of charge Q, so electrons or something of charge Q. And whenever you have charged particles, the following thing can happen. Maybe you inserted your very massive particle, the Wilson loop, of charge K, say. And it can break apart. The massive particle can decay into dynamic excitation. So now there's a consistent way of breaking this apart that reduces the tension, in which you make it end in one of the operators that create these charged particles. So this connects with my comment before that electric excitations in the real world should have a Wilson line attached. So this is the kind of picture. This will be the electric vertex, and you attach to a Wilson line, so you have a gauge invariant object. So one thing that has to happen is that when this breaks, all the charge needs to be absorbed. There's no charge here. So this can happen if Q divides K. If Q divides K, then the charge is not conserved because the loop can break apart. Let's look carefully at how the charge is not conserved. So we can construct the electric measuring charge operator, electric charge measuring operator, this one, sigma 2. Once I break this apart, I can do it without affecting this thing that happens far away. But now, of course, I can contract this through the hole. To the identity operator, and then I can relink. So whenever Q divides K, we find that these electric operators act trivially. They have trivial charge. Okay. This implies that the charges are now set mod Q set. So set Q value. Right? Anything that's 0 mod Q is just not uncharged. And this implies that the symmetry is now set Q. So the simplest case is when you have particles of charge 1, in which you break the symmetry completely. There's just no electric one-form symmetry anymore. So when Q is equal to 1, U1 electric is completely broken. But U1 magnetic survives. Now, when you have charged particles, you cannot be as quick as I was before in doing this calculation. I don't have only the photon in computing this correlation function. I also have my charged particle potential appearing in the loops. So which BEV I get depends on in which phase I am. When you have a charged particle, you can go into a Higgs phase, which is different. In the Higgs phase, the argument wouldn't work. Yeah, maybe not today, but the argument wouldn't work in the same way. You cannot derive the existence of a massless particle, but this is still a Coulomb phase in which the Atoft line in gamma, again regularized, spontaneously breaks the U1M. So you still have a Goldstone boson, you still have a massless particle, and this massless particle is still the photon. So in the Coulomb phase, the photon is protected. What happens in the Higgs phase, if you give a BEV, is that this BEV goes to be 0, and now there's no reason for the massless particle to be there, and indeed it's not there in the Higgs phase. In the Higgs phase, the photon gets a mass. All right. So maybe this is a good point to stop. In the next lecture, we'll start thinking out discrete symmetries, like this one that we just saw, and something about anomalies. See you tomorrow.